All right, good morning, everyone, and welcome to my 11.4 bonus video. In 11.4, we learned about the direct comparison test and the limit comparison test. And as you probably saw in my in-class video, the limit comparison test is my favorite. The limit comparison test takes care of, I'd probably say 90%, maybe even 95% of all of these comparison test style problems. And it's just easier to use. And so that's why the limit comparison test is my favorite. However, some of the times you can't use the limit comparison test. It just doesn't work. And so you need to use something like the direct comparison test. And so that's what I wanted to talk about in this video right here. When do you have to use this direct comparison test? And so maybe some classic inequalities to be thinking about when you're trying to apply the direct comparison test. So that's where I would like to start here. So some classic inequalities that are very useful for the direct comparison test. The first set of inequalities that are very useful, right, are for our trig functions. So sometimes when you have these trig functions, you need to use the direct comparison test, as we'll see here in just a second. And so for instance, if you have something like sine of u or cosine of u, we need to know some kind of classic inequalities that may be simpler than sine or cosine, right? That's the whole deal with the direct comparison test, is that you would like to compare it with something that's simpler. And for sine and cosine, these are both nicely bounded by 1 for the upper bound and for -1 for the lower bound. And this is certainly as simple as it can get, right? Constants, 1 and -1. And so certainly if you can trade something, and I mean, in particular, I'm going to be looking at this function right here, or this series right here, right? Maybe trading in some of these signs in this case for ones or -1s, right? That's going to be making this way simpler. And so, yes, that's a good set of inequalities to know about. Of course, I understand you guys already knew about this, but just kind of having those in your mind. And then the other kind of nice inequality that's good to know about is for the natural log. Sometimes for logs, these don't have a great way to compare using the limit comparison test. And so we need to sometimes use the direct comparison test. And so for instance, if you have the natural log of u, this is always going to be less than or equal to root u. So that's a nice, and by the way, if you just graph these, you'll see that this is true. And the natural log is going to be greater than or equal to some constant eventually. And this is, it gets a little bit hairy here, but we're just going to say 1 here. And so the natural log is going to be greater than or equal to 1. And again, kind of when you're doing these series, you're really concerned about as you go off to infinity. And so this may not be true at the very beginning here, but as soon as you're plugging in a value that's larger than, well, the natural log of e is 1, and e is 2.7-ish or so. So this would be true so long as u is 3 or bigger. So we'll say if u is greater than or equal to 3, this is a true statement. And so, okay, again, kind of these things, we'll see that swapping in for either root u or 1 will end up being very useful. It'll simplify some things down. And so that way we can actually tell if the series converges or diverges. And then the final one, it doesn't really apply to any specific function. I mean, we'll use it for stuff like this where you have maybe a more complicated denominator. But it's just kind of this mini theorem here that says if a is less than or equal to b, and both of these things need to be greater than 0, by the way, then if you take reciprocals, right, kind of the inequality flips. So then, and you can think of this as well as doing some cross multiplication. So, right, kind of bringing this down on the other sides, we'll say 1 over b is going to be less than or equal to 1 over a. So again, kind of you see this flipping going on here. Another way that I think about this is that if you have something that's bigger, right? Well, if you divide by that, you're going to end up getting something that's smaller, right? And so kind of just a quick example here, right? We have maybe that 2 is certainly less than or equal to, but it's certainly less than 5, right? And so if I take reciprocals of those, right, and I have 1/5 and I have 1/2, notice that 1/5 is certainly going to be less than 1/2. So if you divide by less, you end up getting a bigger fraction, right? And so, yes, this will sometimes come in very useful. And so these are some of the nice inequalities that we have for the direct comparison test. Okay, let's go ahead and see how they can be used with a couple of examples. So our first example here, determine if the following series converges or diverges. And again, I invite you to think about trying to use the limit comparison test on this, right? What would you choose for your B sub n's in order to compare with this thing? And you could spend, you could pause the video right now, spend 3 to 5 minutes or something like this, and you'll see basically no matter what you choose, the limit comparison test doesn't do so well, and that sign is really blocking us, right? There's no nice cancellation with a sign. And so it'd be nice to kind of get rid of that sign altogether. And so in particular, I'm kind of interested in this one up here. All right, so let's go ahead and use this inequality to kind of build up the terms of this series here. So in particular, you can see that we don't just have sine, we actually have sine squared. We know for anything squared, it's going to be at worst case 0, but most likely it's going to be positive. So I'm going to go ahead and start off with just a variant of this, saying that sine squared is going to be greater than or equal to 0. And it's going to be less than or equal to, and now technically I have to take this side of my inequality, right, and square it, right? But 1 squared is just 1. So it's not very exciting there. Let's go ahead and multiply by n on both sides. Well, I should say on all sides. So 0 times anything is 0. And then we're going to have n sine squared n less than or equal to n. And then finally, again, kind of my whole goal with this is that I'm trying to recreate my series here. So I'm trying to recreate the terms that I have here. And so to that end, right, I'm going to divide by n cubed plus 2. So divide by n cubed plus 2, divide by n cubed plus 2, divide by n cubed plus 2. So, okay, well, 0 divided by anything is again 0. So I'm just going to go ahead and replace that with 0. And we can see that we kind of have two sides to this inequality, and that's good because it's sometimes hard with the direct comparison test to know what side of the inequality that we want, right? Do we want something bigger than this function, or do we want something smaller than this function? And the answer depends on, well, it depends if it converges or diverges, right? But we don't know if it converges or diverges. And so we're kind of hedging our bets right here. We're kind of carrying around both sides of the inequality to try to figure out, right, which one's going to be useful here. So in this case, right, if I take the series where all of the terms are 0, and I sum those up from n equals 1 to infinity, adding 0 to itself over and over and over and over again, well, this is going to converge. It's going to go to 0, right? Rather boring. And so we have something that's smaller than our original series. So let's go ahead and do the sum right here, smaller than our original series, and this converges. Does that mean necessarily that this larger thing converges? Well, no, not necessarily, right? It's larger. It could still go off to infinity. There's no reason why this would necessarily have to converge if something smaller than it converges. So with that, we've deemed maybe this larger side of the inequality will be more useful in this case. Now, there's two different ways. My claim is that this right here will actually converge. So if I have the series of n over n cubed plus 2, this will actually converge. And there's two ways to show this. One is to use the limit comparison test, right? Because this doesn't have any signs in it, we could actually do the limit comparison test with this. And we would compare it with, let me just kind of go off to the side here. Again, taking kind of the largest power for the numerator and the denominator, or each factor here. The largest thing in the numerator is n, and the largest thing in the denominator is going to be n cubed. And so this is going to simplify down to 1 over n squared. So this is going to converge because of the p series, right? And so therefore, by the limit comparison test, this thing will converge, and therefore by the direct comparison test, we'll actually be able to show that our original series will converge. The other option, right, is to continue using the direct comparison test. And in particular, I would like to get maybe a little bit of practice using this right here. So notice with the direct comparison test, because I have a +2 in the denominator here, my claim is that this is going to be less than or equal to n divided by n cubed. So notice that when I divide by more, again, thinking about this as, actual numbers there, we see this +2. So, this is like my 1/5, right? Versus if I divide by less, this is thinking about it like my 1/2 sort of deal, right? 1/5 is going to be less than my 1/2. So because I've taken away, in this case, 2, right, we're going to end up getting a smaller fraction. And so if you want to set this up in all of its formality, right, you would say, we have, whoops, that's not my pen. We have n cubed is going to be less than or equal to n cubed plus 2, right? By adding 2, we're actually going to get something larger. And so therefore, when you go ahead and you take the reciprocals of these things, remember you need to flip the inequality or flip the sides here. So I'm going to go ahead and flip these. And that's why this is true. Now you can just multiply through by n on the top, n, right? And you get exactly my statement from below. So, okay. In fact, let's go ahead. We can just leave this here. All right. So with this, right, again, this one up here is going to be equal to 1 over n squared. And if we go ahead and sum these up, right, consider the series 1 over n squared, we know that this converges by the p-series test. Oops. Converges by p-series. And so now we have something that's larger than our original series, right? Greater than or equal to, larger than our original series, and it goes to some finite number. Is there any way then that this right here, or I guess really even better, one down here, our actual original series, is there any way that this could go off to infinity if something larger than it goes to a finite number, right? I don't know what this goes to. Maybe it goes to something like 5, right? Or maybe like 2 or whatever, right? Is there any way that something smaller can go to infinity then? Well, no, it's got to be less than 5 or 2 or whatever this thing converges to. And so this must converge by the direct comparison test. So we know this larger thing converges by p-series. And so maybe over here, I'll just write my conclusion statement. So by the direct comparison test, our original series, n sine squared n over n cubed plus 2, summing from n equals 1 to infinity, converges. And I already said, right, by the direct comparison test. We saw that something larger than it converges, and so this thing has no choice, right? There's no way this can get to infinity if something larger than it goes to a finite number, like 5 or 2 or what have you. So yes, this must converge. All right, so that would be my final answer, right? We've determined that our original series converges. One more of these here, and then I got kind of one more that doesn't really fit into any of these categories here. Give you something to think about. Okay, determine if the following series converges or diverges. And in this case, I have the natural log of n divided by n cubed. And we're starting at 3 and beyond. And so, well, you can see we're starting at 3. That's very convenient. Certainly, if we started at 4 or 5 or anything like this, it would also be, equally convenient here. This is one that, again, if you spend some time, try to use the limit comparison test on this, right? Don't take my word for it. Try and see what happens, right? My claim is this natural log kind of ruins things. It's hard to make it go away. And so, well, it's hard to make it go away and choose anything simpler than this, I guess. So the direct comparison test will be very useful here. Again, I don't know if I need something larger than this or smaller than this. And so I'm going to carry around kind of both sides of my inequality. So I'm going to say that this is going to be greater than or equal to 1 and less than or equal to root n. Again, I'm trying to come up with a statement about this particular series right here. I kind of isolated the most difficult part, this natural log. This is the main issue. And that's why I kind of start my inequality with that. Plus, this is one of the things that I have in the box up here. And now I'm going to try to build my series similar to what I did last time. And so I'm going to divide by n cubed. And of course, when I do that, I need to do this across the board. And let's see, on this right-hand side here, this root n divided by n cubed, this will cancel out a little bit. Remember, root n is the same thing as n to the 1/2 power. And so there's going to be a little bit of canceling that goes on, and we're going to have n divided by 3. And again, we need to subtract away 1/2 from the canceling that happens here. And this is going to be n raised to the 5/2 power, or that's the same thing as 2.5, of course. So I'm going to go ahead and just put that this is the same thing as 1 over n to the 2.5. Okay, and so now we can go ahead and take a look at this. If I consider the series with 1 over n cubed, I know again that this converges by p series. And since this thing converges by p series, right, is there any way that a larger thing could diverge? And the answer is yes, it's larger, right? Just because a smaller thing goes to a finite number, it doesn't mean that a larger thing couldn't go to infinity. And so sadly, this doesn't end up being useful in this case. But again, I didn't really know that until, right, I'm kind of in the middle of this. On the other hand, right, if I sum up 1 over n to the 2.5, this converges also by p series, right? P series is very nice. And right, the p is greater than 1 here. 2.5, the power of my n here, is greater than 1. And so that I know that this converges by p series. And so since this larger thing converges by p series, is there any way that a smaller thing can diverge? And the answer is no, right? If this thing goes to a finite number, there's no way that a smaller thing could go off to infinity. And so this right here must also converge by the direct comparison test. And so let's go ahead and give our conclusion statement. So I'll say since, and just kind of reiterating here, 1 over n to the 2.5 converges by p series. And this is a nice larger thing. We know that our smaller original series, natural log of n divided by n cubed, must also converge. And this is going to be because, well, the direct comparison test. And you can specify, right, your starting bounds and all that sort of stuff, but usually I have not seen points kind of taken off for this. If you don't do your starting bounds and all that. And it'll be true either way, no matter what your starting bounds are here, so long as you're not dividing by 0 or something like this. Okay, there is example number 2. For our last example here, I'd like you to go ahead and pause the video and think about this one for a minute, and then we'll come back and do this one together. All right, so I hope that you were able to come up with, even though I didn't give you kind of the inequality for this, because honestly, I haven't seen arctangent come up so much. This is a problem that I created just to show you that there is, of course, more out there. I gave you kind of the classic inequalities that you need for the direct comparison test. But, and then I thought, okay, is there any other kind of inequalities that maybe I could come up with that don't really fit into this, but you could turn into a direct comparison test sort of problem? So again, I claim that this has the same sort of issues that the other problems had, where you can't really use the limit comparison test on this one. However, if you think about arctangent, right, we know that it is bounded between negative pi over 2 and pi over 2. Those are its horizontal asymptotes, right? And this came up a decent amount in chapter 6. So because also we know that this is kind of positive, and again, kind of I'm thinking a lot about what our arctangent looks like. It's like it's our tangent, but it's turned on its side, right? And so we have these asymptotes going off in this direction at pi over 2. And oops, those are kind of low. Let's start up here. These ones down here going off to negative pi over 2 if you plug in negatives. Now we're plugging in 7 and bigger, 7, 8, 9, right? Because our starting bound here is at n equals 7. And so, in fact, we can do a little bit better than this. We know if you're plugging in positive numbers into arctangent, we can go ahead and say that this is going to be greater than or equal to 0, right? In fact, it's strictly greater than 0. And this is going to be true anytime what you're plugging into this is going to be greater than 0. So I'll say since n is greater than 0, we know that this inequality here is true. Now, again, similar to our other ones, we need to try to build this entire term right here. And so we're going to divide through by n raised to the 5/4, it looks like. So divide by n to the 5/4, divided by n to the 5/4, divided by n to the 5/4. And of course, 0 divided by anything will be 0. Again, this one, I guess I chose all problems that converge. Maybe I should have mixed it up a little bit here. But we are going to need to look at this bigger one here yet again, because, right, summing up pi over 4 divided by n to the 5/4. Well, this would be equivalent to, right, we could pull out this, oh, I said pi over 4 there, I meant pi over 2. We could pull out this pi over 2 using our rules of series there. And then this is summing up 1 over n to the 5/4 is the same thing as 1.25. So this is going to converge by p series. And so since a larger thing converges, a smaller thing will also converge. So our smaller original series, which was more complicated, converges by the direct comparison test. All right, so yes, again, in this video, we covered the direct comparison test quite heavily. Make sure that you watched my pre-class video and my in-class video where we cover the limit comparison test in great detail. Again, that's going to work for 95% of the problems out there. The limit comparison test is very, very powerful. But there are cases where you do have to use the direct comparison test. There are cases where the limit comparison test does not work. And so you can't completely just ignore or forget about the direct comparison test. All right. Thank you so much for watching, everyone. I hope you have a wonderful day. I'll see you out there.